Ever wondered what the future holds for the world of material science? Imagine materials that can repair themselves. This isn't science fiction, but a transformative advancement known as self-healing materials. These innovative materials hold the potential to dramatically reduce maintenance needs across various applications, but the journey isn't without its challenges. The key hurdle is creating materials that can self-heal effectively and repeatedly under different conditions. Join us as we explore this fascinating frontier in material science. First up, we have polymers, a versatile class of materials that can be engineered to self-heal. Polymer-based self-healing materials typically repair themselves through chemical reactions. When a crack forms, it triggers a reaction either within the material itself or between the material and an external agent, effectively sealing the crack. But these materials are not without their challenges. For instance, some of these materials can only heal once, or they might require specific conditions, like heat or light, to trigger the healing process. The healing capacity is also often limited. Researchers are exploring potential solutions to these challenges. One approach is to develop polymers with microcapsules containing healing agents. So, when the material cracks, these capsules break, releasing the agent which reacts with a catalyst embedded in the matrix. There's also research into multi-healing systems that can heal repeatedly and under various conditions. While there's work to be done, the future of polymer-based self-healing materials looks promising. Moving on, we delve into the world of self-healing metals, concrete, and ceramics. Let's start with metals. Metals can be made self-healing by embedding healing agents within microcapsules or vascular networks. However, the high temperatures often needed for metal repair can damage the surrounding structure. The solution? Researchers are investigating lower temperature metal alloys and shape memory alloys. They're also exploring the use of ultrasonic waves to aid in the healing process. Next up is concrete. By incorporating bacteria that produce limestone when exposed to water and air, concrete can essentially fill in its own cracks. But maintaining the viability of these bacteria over long periods and in varying environmental conditions is challenging. The solution lies in using bacterial spores, which are more durable, and pairing them with nutrients encapsulated within the concrete. Different bacterial strains and encapsulation techniques are also being researched to enhance longevity and effectiveness. Lastly, we have ceramics. They can self-heal through a process called sintering, where heat is used to fuse cracked surfaces. But with high energy requirements and potential damage to the material's integrity, there's room for improvement. Scientists are exploring low-temperature sintering processes and the use of nanoparticles to facilitate the healing process. These materials are pushing the boundaries of what we thought possible, bringing us closer to a future where maintenance could be a thing of the past. But what about electronics? Could they self-heal too? Imagine a world where a cracked circuit board isn't a death sentence for your device. For electronics, self-healing means mending conductive pathways. The main challenge lies in re-establishing electrical conductivity in complex circuits. The solution? Embedding microcapsules filled with conductive ink in the circuit board. When a crack occurs, these capsules break and the ink seeps out, filling the gap, and voila! The circuit is restored and your device is back in action. But here's another hurdle: scaling self-healing materials for widespread use. It's one thing to create these marvels in a lab, quite another to mass-produce them. Collaborating with manufacturers to develop feasible production methods is key. By focusing on integrating self-healing properties during the material synthesis stage, rather than as an afterthought, we can make these materials more accessible. Although challenges remain, the potential for a world with self-healing electronics is an exciting prospect. As we push the boundaries of material science, we must also consider our impact on the environment. It's crucial that the production and breakdown of self-healing materials are environmentally friendly. Using biodegradable materials is a start, and we must ensure that the healing agents and processes do not produce harmful byproducts. This journey has taken us through self-healing polymers, metals, concrete, ceramics, and even electronics. Each material has its unique challenges, but innovative solutions are being developed every day to overcome these hurdles. From microcapsules containing healing agents to the use of bacteria and nanoparticles, the possibilities are as diverse as they are fascinating. As we move forward, the focus is on integrating these self-healing properties during the material synthesis stage, not as an afterthought. The road ahead is full of challenges, but the potential rewards of self-healing materials are immense. Stay tuned as we continue to explore the future of material science.